Okay, let's talk about the data that you should have gotten for the specific heat, and I'll put it right here. And so this would be your data if you were able to write down those numbers as I was explaining them. And so here's our first experiment: brass, and then aluminum, and then lead, and then the mass of the waters, the mass of the metals, the initial temperature, and then the final temperature each time. And so let's go ahead and then fill this in and then see what numbers you got, the specific heat. And then we'll see how close we get to the accepted value. And if you noticed in the video, I said that we tend to get a little bit smaller here in our measurements than the actual value. So we'll see what we get. In fact, maybe I'll just put down here what we were hoping to get. I'll look at Appendix B, and if you wanted to look in Appendix B, they'll say that 0.092 calories per gram for each degree is the ideal goal for brass. Aluminum is 0.22 calories per gram for each degree. And lead is the smallest, 0.031 calories per gram for each degree. So that's kind of what we'll hope for here. And so let's go ahead and do the calculations. And as you saw me working on the board, maybe the first step is to say that the heat coming out of the hot piece of metal is equal to the heat that goes in to the cool water. And that's the conservation of energy, where on the board I had, this little diagram here. We had this cool water, and then we put a hot piece of metal inside of it. And so the metal was hot, and the water was cool, and so the conservation of energy said those should be equal. In fact, that's really the answer to your first discussion question here. It says, how does the amount of heat exchanged by the water compare to the amount of heat exchanged by the metal? And so the short answer is they are just the same. It's a conservation of energy principle. And so that's what they want you to think about as you do this calculation. And if we look at the second question, that's kind of this first step here. Maybe I'll pull the questions away and then come down to here. But it says here, how was the amount of heat exchanged by the metal actually calculated? So in other words, how are you going to get this number? How are you going to get the energy that came out of the metal? And the answer is we're going to calculate what goes into the cold water. And so that's the answer here to this question. How was it calculated? Maybe I would just here by the amount going into the cool water. So that's what they're kind of getting at here. And so let me actually then do this calculation, and we'll see what kind of a number we get here. And for the brass, anyways, we would come over here and say, okay, so here's the water. So the mass of the water for the brass was the 71.6 grams. The specific heat for the water was the famous 1 calorie per gram per degree Celsius. And then the change in temperature of the water would be the 39.2 minus the 19.8. And so let's see what kind of number I get here. And so grabbing my calculator here, I'll go 39.2 minus 19.8. So that's the change in temperature times 1, not really necessary, times 71.6. And so this comes out to be 1389.04 for the amounts that goes into the cool water. And of course, now the other side of the equation, as you saw on the board, would be these MC delta T, and all of this then would be for the metal. So if we take this 1389.04, and we're looking for this, the specific heat of the metal, this change in temperature was the hot metal 100 minus the 39.2, and the mass of the metal was the 269.7. And so I can get actually the specific heat for the brass by then taking that number and first dividing it by the 269.7, and then dividing that by 100 minus 39.2, coming up with 0.0, and I'll call it 85. And so I'll put that right here, 0.085. So hopefully that's the number you got. And you can see I'm kind of close, but a little bit low, as I kind of expected I would get. And so I can do a percent error. That would be the difference in the numerator over the, I'll call it the correct value. And that's a fraction, so times 100 makes it a percentage. So we're pretty close, but percentage-wise, we're probably not all that close. Let's see. So this is the 0.85, and then if I subtract the 0.092, that's how much I'm off. And I won't pay any attention to the negative, but I'm off by 0.007. And then out of, and so here to divide by the correct value, the 0.092, and then to change it into a percentage, gives us at about a 7.9% error. So, a reasonable number, typical number. So, that's hopefully then your calculations. In fact, it kind of leads to this third question here on the worksheet, which says, how does the change in temperature of the metal compare to that of the water? And I didn't do it individually here. Maybe I'll come back and do that, but 100 minus the 39.2 is a change of 60 degrees, whereas the water only changed by 39.2 minus 19.8, 19.4. And this general question, you can see that all the way through. There's a very little change. I mean, like there's under 20. And then again, this is just barely 10. Whereas the change of the water, I mean, that's almost 70, and that's a little bit more than 60. And so they want you to notice that the metal is changing a lot more in its temperature. And it really boils down to the specific heat. You can see that the total energy is a combination of all three of these. And since the energy coming out of one equals the energy going into the other, things with small specific heats, and so all of our metals have a small specific heat compared to one, which is for water. And so that's saying water has a lot of energy for one degree of temperature change. So in other words, water stores a lot of energy, and that's what they want you to notice. And so when they say here, how does the change in temperature of the metal compare to the water? You can just say a lot more. And then, of course, that is this, why is there such a large difference? And then you can say here, because the specific heat of water is much bigger than the metals. And then trying to give you some insight here to make you realize, if we come back to these calculations, that the energy change, although is the same, it doesn't mean the temperature is the same. And so it doesn't take nearly as much energy to change 1 gram of brass compared to 1 gram of water. In fact, you can kind of see in this number, if we just round that to 0.1, it takes 10 times more energy to warm up 1 gram of water than it does 1 gram of brass. And that's what they're trying to get at here, is there's just an enormous large specific heat. And that's a long way of saying that really the specific heats for your metals are kind of low. They don't take much energy to change their temperature, but it takes a lot of energy to change water. In fact, that kind of leads into these last set of questions. See, how does the large specific heat of water help explain Santa Barbara's moderate temperature? And I would just, basically say because of the large specific heat, and also because of the large amount of water in an ocean, so I'll put both of those. The mass is large and the specific heat is large. Just to change the temperature of about 1 degree in the ocean would be an enormous amount of energy. And because of that, the ocean doesn't really change its temperature by much. It's very stable. And then, of course, the air that rests on top of the ocean will get about that same temperature. So here in Santa Barbara, in wintertime, we might get the ocean to go down to, I'll do Fahrenheit since I know that one better, but, 55 degrees Fahrenheit. And then in the summertime, on a good summer day, it'll go up to 70 degrees Fahrenheit. But see, that's a small range. And so basically what that really means is that if the air temperature in the summer got more than 70, the fact that it's sitting on a cooler body of water below 70, or even, most of the time it's about 65 really, it'll always cool down to 65. So it's difficult for Santa Barbara really to stay and remain above 65, 68, 70 degrees. To ask Santa Barbara to get up to 70 degrees is a challenge, because it's just constantly being cooled down by the ocean. But notice it says Santa Barbara's moderate temperature, because it works the other way in the wintertime. Even what might feel like it's cold to you when you get in the water at 55 degrees, but what that means is if the air ever got lower, say a cold front moves in from Alaska and that cold air is under 55 degrees, because it's in contact with a large body of water which has an enormous amount of energy, it'll warm it up. It's got plenty of energy to warm it up. The ocean really won't change its temperature, but it'll definitely change the temperature of the air. And then it's difficult for the air temperature to really stay below about 55 degrees. So it's, Santa Barbara getting under 55 or Santa Barbara over 70 it's not common. Obviously it happens, but at the time it happens, the ocean is always fighting it one way or the other, trying to warm it in the winter or cool it in the summer. So anyways, that's a long-winded way. It says, how does the large specific heat, explain? And you can just say, this makes the ocean's temperature about the same year-round, I guess. This might be one way of saying it. Or you might say it makes it's stable. It makes the air temperature stable. Or you just might say, it tries to get the air to be the same temperature as the ocean, and the ocean won't change by much because of its large specific heat. And then, of course, hopefully the other parts you got out of this is discuss what effects the following errors would occur in your calculation. And we could come back and look at our formulas, but I think we can do better by just looking at the concept of it. It says heat is transferred through the calorimeter walls. And what that means is when you put the hot piece of metal into your cool water, we had this styrofoam cup, and I didn't use the fancy word calorimeter, but these are where the calories were exchanged. And so if energy was leaking out and basically the hot metal was warming the room, that would come across as if there was less energy being stored in the metal, and so this would make a lower specific heat for the metal. See how the heat transfers through the wall. Again, to just make it look like it has less energy. So the idea here is you're thinking of specific heat as a measurement of how much energy is stored or needed if you're warming it up, but in this case we're cooling it down. So when the metal cools down, how much is stored, how much has to be released. I'll jump down to C because you can get that same answer. The metal sample cools while it is being transferred, and so kind of in the same picture, again, if we were to lose energy as we were bringing it over, and we did, and that's why I think we always get low numbers here compared to the real thing, is we lose so much heat. Just bringing it over. I tried to do it very quickly, but just bringing it over, we lose it. And so we lose it here, and I think we also lose it through the styrofoam also. And so we always get a lower number here. And so, again, that's going to make a lower specific heat because, again, this a good way to think about the specific heat is kind of this measuring device, how much energy is stored per each degree it changes. Now, a problem that I didn't really address, and we don't usually have this problem, but they ask about it, what if water clings to the metal sample? And so if you come back here and say, okay, now, as you were carrying it over, there was some water sitting on top. And I'm sure there was some water sitting on top, but that would be carrying extra energy. And then when you put it into here, that would be warming it up extra. And so that would come across in your calculations and in your equations as if you had extra energy. And that's what specific heat means. And so this would make a higher specific heat. And so that's kind of the meaning behind that set of questions. Now, with that in mind, I should finish up here with these calculations. And so let me put my calculator here and see if you can see it on the screen. I think you can see it there. And say, all right, let's do that for the aluminum now. Let's do that same first step. We're going to calculate how much energy came out of the metal by saying what went into the water. So we need the mass of the water, 69.9. We need to multiply it by the specific heats of water, that's 1. Then we need to multiply by the change in temperature, and so this would be 36.4 minus the 19.8, and I'll just put that right here for the aluminum, and so this would be 116034. So that's the amount of energy that would go into the water. And that was that first question. They're the same, and that's how we calculate it by saying, okay, what went into the water then went into the metal. So then if you recall, to get the specific heat, we needed to do 2 steps. The first one was we needed to divide it by the mass of the metal. So coming over here to aluminum, it was 91.6. And the other thing we needed to do was divide it by the change in temperature of the metal. And so it was at 100, and then it cooled down to 36.4. And so I get a specific heat of about a point, looks like 199. And again, you can see that we are a little bit under and kind of our normal number. Again, because back here, we seem to always get a lower number because we seem to lose energy through that calorimeter wall. And I think most of it's actually on the transfer over, but also the styrofoam cup. We might even carry a little water with us, but those don't balance each other. That makes it a little higher, but it's really those two. And of course, now if we did a percent error, let's subtract the 2. So 0.22 minus what I just got. I'm that much off. out of the 0.22 and then multiply by 100, and looks like this one's off by about 9.5%. So good, and still under 10%. That's always good to know, because I always tell students if you're under 10%, you're doing well. Usually they do a lot more than that. Well, get this last one done here and we'll be finished. And so if I again come over here and then say, okay, for the experiment with the lead, we need the mass of water. This time it was 71.2 multiplied by 1 times the change in temperature, which was only a 29.7 minus a 19.8. That's the amount of energy that then went into the cool water, coming, of course, from the lead. So if we then divide that answer by the mass of the lead, 354.7, and also divide that by the change in temperature of the lead, so that'd be 100 minus 29.7, we get a number of 0.028. And again, you can see a little bit low, as we seem to always be, and that's again probably around my 10% mark. Let's see, 0.031 minus that last answer. So that's how much I'm off out of 0.031, and times 100 gives me about my 8.8%. So we're a little low again by just under the 10%. But I'm glad to see we're under by 10%. That's always rewarding there. All right, and that will conclude our first lab, both the directions and the answers. Bye.